All right. So now that we're familiar with the different levels of measurement, as discussed in chapter two, let's talk about some. Let's talk about a very important component of any measurement instrument, which is reliability. So reliability is simply whether a test, um, or whatever it is that you're using as a measurement tool is measuring something consistently. And what's cool about this notion of reliability is that it's based on the separation of different components of what makes up any particular test score. So the test score um, consists of the observed score, which is what you actually got on the test, the true score, which is the accurate reflection of what you know, and the error score, which is the difference between the true score and the observed score. So, in other words, your observed score is your true score. Oops. Your observed score is the true score plus your error score. And it's important to note that the observed score can only be equal to the true score if we measure the trait without any error. But unfortunately, it's highly unlikely that we can measure anything without error. And so, an implication of this conceptualization of reliability is that error becomes a very important thing to understand if you want to get a good hand on reliability. So specifically, as error increases, reliability decreases, and vice versa. So this is why it pays to be deliberate and careful when we're developing a measure. You want to reduce as much error as possible in order to increase the reliability of your scale. Now let's take a moment and then go one step further. Let's talk about error and break that apart. So the error part um, consists of two types of error. One is called trait error, and the other is called method error, both of which contribute to differences between the true and observed score. So trait errors are sources of errors that reside within the individual taking the test, such as, I didn't study properly, I forgot to set the alarm, I'm feeling really poorly, and that is affecting your scores. And then you have the method errors, so sources of error that reside in the testing situation itself, basically not within that individual, so lousy instructions, a terribly hot room, so on and so forth. And so, for the purposes of the exam, we definitely want to know how do you distinguish between trait and method error. That's pretty straightforward, I think, so that you can identify examples accordingly. So that's basically it. As the error component gets smaller, reliability increases, as you can see how this works in this equation over here. As the denominator in this equation gets smaller, the results of this equation, which is reliability, becomes larger. So our job is to create an instrument um, that reduces the sources of error as much as possible. Now the other thing about reliability is this. So I just gave you pretty much a classical approach or a model or a classical model of reliability, but there's also another model that you should at least know about, and that's called item response theory. Now, for this chapter right now, you don't need to know this in a whole lot of detail, but just enough for you to know that IRT is based on the idea that the likelihood of a correct response is a function of the person taking the test and characteristics of the item. It's also called latent trait theory because the individual's trait play a very important role in how they perform in the test. So we'll get to this material in greater depth in chapter 6. But for right now, you should probably know that IRT is an alternative approach to modeling reliability, a little bit more modern approach, and it's also called latent trait theory. So reliability is measured. So back to the classical measurement land over here. We're no longer talking about IRT. According to more classical methods of conceptualizing reliability, reliability is measured through a correlation coefficient, which is a numerical index that tells us how closely two variables are related to one another, such as two administrations of the same test. So more accurately, how much the variables share or have in common. For reliability purposes, the correlation coefficient tends to range between 0 and 1. So the higher the positive number, the more reliable the test scores. You may recall, maybe from another basic statistics class, that, and you probably learned this in high school as well, or at least I hope you learned this, that the range of a correlation coefficient is actually -1 and +1 instead of 0 and 1. So what's the difference over here? What is the difference between a reliability coefficient and a correlation coefficient? Well, a test with a coefficient that is a test with a reliability coefficient that is less than 0 or negative has pretty much non-existent reliability conceptually. So reliability coefficients are only worth considering really if they are positive. And so be sure you know this as well, the concepts of reliability, um, and how it's measured, and the range of a reliability coefficient, and how this may be different from the more general form of a coefficient, which is the correlation coefficient. So reliability can be computed in many different ways, and we'll cover the four most important and most often used in this section. So for the purposes of this exam, you want to make sure that you study these four forms of reliability: test retest, parallel forms, internal consistency, and Interrater reliability. So let's talk about each type of reliability in a little bit more detail. So test retest. Test retest reliability is used when you want to examine whether a test is reliable over time. So for example, if you want to evaluate the reliability of a test that examines the preference for different types of vocational or job training programs, you may then administer the test in September and then re-administer the same test again, maybe in November, and then you correlate the two sets of scores. You correlate the scores from a test given in time 1 with the same test given in time 2, and that provides you with an estimate of test retest reliability. Test retest is a must when you are examining differences or changes over time. The biggest critique of test retest are two things: practice effects and time, and sometimes the interaction between the nature of what you're trying to test and how that interacts with time. So let's talk about practice effects. So, for example, you may have test takers in the first testing. Test takers may remember the questions, ideas, or concepts that you are measuring in the first time of testing, and that may have an impact on the second testing and their score. So if you're trying to so let's say you got a test on memory and you get them to memorize a list of 20 words. You test them in September and then you test them, say, in October. If it's the same exact questions that you're asking them to memorize again, obviously they would do better on the second time. And so there are carryover effects that you need to be mindful of. This is somewhat addressed with the test of parallel forms, but we will get to that in just a little bit. When it comes to test retest, one of the issues is practice effects. The other is the interaction between the amount of time between tests and the nature of what you're trying to sample. So let's say you have a test that measures motor skills in infants, and let's say you measure test retest for infants ages 3 months, and then you wait another 3 months and you measure those same infants again when they're 6 months. Now, you probably will not get a very high reliability coefficient between 3 months and 6 months for the same set of infants, not because the test is unreliable per se, but you see dramatic changes in their motor skills. So depending on the construct that you're trying to measure, you want to make sure that the construct that you're trying to measure is at least theoretically supposed to stay the same between the time window of your first time of testing and the second time of testing. And some constructs are supposed to stay the same in a certain time window, and some not. So it just depends on what you're trying to measure. Another example would be um, say the amount of present moment anxiety, right? Anxiety kind of if you're not talking about any endogenous anxiety disorders, if you're just talking about daily types of regular anxieties that we have, you know how anxieties fluctuate up and down, and so even you kind of want to be precise in what you're trying to measure and be aware of how that construct may interact with time and may influence the results of your reliability measurement. So thank goodness test retest is not the only way to measure reliability. It is a very important one, um, but not the only way. So another form of reliability is parallel forms of reliability, and this is used when you want to examine the equivalence or similarities between two different forms of the same test. So let's go back to that example about you have a memory test that's based on 10 different words. And then you memorize them as best as you can, and then you recite them back after 20 seconds of study. And as with any good scientist, you want to make sure that the reliability of the test is tested. Now, so you create another list of words, right? Another list of 10 different words that is similar to the first list in terms of task demands, but obviously different in terms of content. And so you then correlate the two scores from the two different forms to get some sense of how consistent these two different versions of the test is. So it's the same ideas that are just being tested, just in different forms, and it does uh, um, address the practice effects that you would get with test retest. And I'm sure you've met professors or instructors who have done this before, where they would administer different versions of the same test. Typically, they would have had tested the parallel forms reliability. Are they the same in terms of the overall level of demands or difficulty? So far we talked about test retests, parallel forms. Let's talk about internal consistency. So it's another way to measure reliability. It's quite a bit different from the previous two types of reliability. Internal consistency is used when you want to know whether the items on a test are consistent with one another, in that they represent one and only one dimension, or one construct, or one area of interest throughout that test. And so there are several ways to establish internal consistency. Specifically, we'll talk about split half reliability. That's my mouse. Split half reliability, Cronbach's alpha, and the Richardson 20. So for the purposes of this exam, you want to make sure that you know the different ways of establishing internal consistency so that you can identify based on the description or the examples given. The other thing to consider about internal consistency is, let's say you got a measure that is composed of 5 different subscales, and they all measure, say, quite different constructs. If you were to, say, sum the average or the total scores for each of the subscales and try to measure internal consistency for those 5 different subscales, you may get a very terrible internal consistency finding, because you're measuring 5 pretty different constructs. So this is typically only applicable to subscales, or if it's a total score, typically a total score that is not composed of too many different subscales that are disparate from one another. So let's talk about split half reliability, the first way of measuring internal consistency. So this is the most simple way to establish internal consistency. And so what you do is you split the test into two halves and then compute what is called the split half reliability coefficient. And here the scores on one half of the test are compared to the scores on the second half of the test to see if there is a strong relationship between the two. And so if there is, we can then conclude that the test has internal consistency. But how do we split the test? It's usually best to select all the odd items and all the even items. So it's semi-random, not really random, but um, uh, you're trying to make sure that there aren't any particular aren't any particular factors that may distinguish one group of items from the other. So what you don't want to do, for example, is to group, say, the first half question. Let's just say you got 20 items in a scale. You don't want to group the first 10 into one group and the last 10 into the other group, because you may have fatigue starting to come in towards the later end of the test. This is especially relevant for tests that have hundreds of items, and so by selecting odd or even items, that kind of helps spread out um, any particular fatigue or any other particular grouping effects. You have certain items that may be more difficult than others or something. um, the odd even is a pretty simplistic way of dividing your test into two. Um, now, when you compute the correlation coefficient between these two half of tests, you need to correct this reliability coefficient with the Spearman-Brown formula to account for the fact that your reliability values came from a test that was basically cut in half. Because according to classical measurement theory, pretty much the more longer your scale is, the more items your scale has, your reliability tends to increase. And so if you are getting a correlation from two halves of the same test, you then need to correct for that using the Spearman-Brown correction. Here's the second way of computing internal consistency, probably more common in most papers that you would read in papers today. And this reliability coefficient is especially useful when you're looking at the reliability of a test that doesn't necessarily have a right or wrong answer. But it also works nonetheless for tests with right answers as well, but it's more flexible in that sense. So the formula to correlate Cronbach's alpha is to divide the number of items. So let's say you got a 20 item measure, so that's 20 divided by 20 minus 1, and you multiply that ratio by the difference between the variance associated with the observed score minus the sum of all the variances for each item divided by the variance associated with the observed score, and that ratio then is going to be multiplied by k divided by k minus 1. This is essentially the same conceptually as computing all possible split halves of the test and then averaging all those split halves of the test. So that's pretty cool. So this is the one reason why most people just do Cronbach's alpha as opposed to split halves, because you are computing all possible split halves of the test. You get a chance to compute this in Excel on your own. There's a video tutorial that is provided in Moodle for the first quarterly assignment. So be sure to watch the video, test it out on your own with the example, and then work on the quarterly assignment. And just let me know if you have questions. Last but not least, we have the Hugh Richardson 20, which is computationally similar as Cronbach's alpha, but it's used when answers are dichotomous, such as right or wrong answer or true or false tests. The formula is basically, again, very similar. So n divided by n minus 1, so the number of items on the test divided by the number of items minus 1, and you multiply that ratio by the difference between the variance of the total test scores, and you multiply that with the sum of the product of the percentage correct and the percentage incorrect on each item divided by the variance of the total test scores. You get a ratio for that, and you multiply that by n divided by n minus 1. And your textbook gives you a very nice example to help you walk through that. Again, computation is similar as Cronbach's alpha. I think the example in the textbook illustrates it pretty simply and nicely. So go ahead and take a look when you get a chance. Now, so far, we've talked about internal consistency, right? And that can be measured by various indices such as the Hugh Richardson, Cronbach's alpha, split half. We talked about parallel forms of reliability, and we talked about test retest. All of those reliability indices has had to do with the reliability of the instrument. So for this particular type of reliability, this is about the reliability of those administering the instrument. So this is typically for any type of instrument that requires a rater or a judge to kind of score whatever it is that you're trying to score. So we measure inter-rater reliability when you want to know how much two raters agree on their judgments of some outcome. And so one example that I can think of was back when I was an undergrad, we went to Head Start centers, and we basically measured the frequency, the number of times specific types of behaviors occurred in classrooms on a 30-second interval for a particular period of time that was randomly selected. And to make sure that my judgments of whether or not a behavior occurred, such as, not listening to a teacher, picking on a friend, I can't remember the exact constructs. They were much more precise than that. To make sure that my judgments on whether or not particular behaviors occurred were good or more were reliable, we got another rater to also make the same ratings when I was making those same ratings as well. So that's kind of what we mean by inter-rater reliability. So the formula is basically the number of agreements divided by the number of possible agreements. And because it's basically the number of agreements, the threshold for good inter-rater reliability is usually higher compared to other types of internal reliabilities, which brings me to my next slide. So in a nutshell, we want two things really when we're interpreting reliability coefficients. We want reliability coefficients first of all to be positive, and second of all, we want reliability coefficients to be as large as possible. Remember, it ranges from 0 to 1. In general, and acceptable reliability is 0.7 or above, much more acceptable if it's 0.8 and above. But when it comes to inter-rater reliability, we really should expect nothing less than 90%, because if it is less than 90%, all you need to do is just train your raters more, or maybe revise your item descriptions to make sure that the operationalizations of specific behaviors, for example, are more clear-cut and not vague. So for the purposes of exam, make sure you know what are the thresholds that we're looking for most types of reliabilities, and how that might differ for inter-rater reliability. Another way to understand and conceptualize reliability is through the use of the standard error of measurement. Your standard error of measurement is a measure of how much inconsistency or error one might expect in an individual's observed score. It's basically the amount of variability you might expect in an individual's true score if that test is taken an infinite number of times. So the higher the reliability of the test, the lower the standard error measurement. And a lot of times test scores or intelligence IQ scores or achievement scores, they use this concept quite a bit, the standard error measurement, to give users a sense of how much confidence they can have on the precision of a test score. So for example, you may remember in your basic statistics class in maybe high school, that one standard deviation covers about 68% of all scores that are distributed under a normal distribution. What do you mean by normal distribution? Well, we assume, for example, that if you look at IQ scores across the nation, for instance, that it is normally distributed with most scores kind of concentrated about around the average, and then you get less scores occurring on the more extreme ends of the IQ score. So like 130 or more, or what's 85 minus 15? 70 points or more. But basically, if you just Google normal distribution, you will get a visual depiction of what I mean by how scores tend to clump together in the middle. So one standard deviation covers about 68% of all scores under a normal distribution. So that is actually in towards the middle of the distribution. Tell you what, let me just Google that right now. Oops. Okay, normal distribution. Let's see if we can find some pictures over here. There you go. Great. Normal distribution. This is what I'm talking about over here. So 68% of all scores kind of clump together in the center. So one standard deviation plus 1 minus 1. One standard deviation covers about 68%. So in other words, for about 68% of the observed test scores tend to fall within plus minus 1 standard error measurement of the true score. 95% fall within plus minus 2. So if you sum 13.5, 13.5, 34 and 34, you get 95%. 95% fall within plus minus 2 standard error measurements of the true score, and 99%, so all of this basically up to -3 and +3, fall within -3 and +3 standard error of measurement of the true score. So a lot of times the people who make the tests, they would use your standard error measurement to calculate what we call confidence intervals, to give users a sense of how much confidence you can have that a score truly is the score that you're seeing. So back to the slides. And over here you can see in the equation how reliability is part of the equation for calculating standard error measurement. 1 minus reliability, get the square root of that, multiply that by the standard deviation, and you get 1 standard error measurement. And you multiply that accordingly to get 2 and 3 standard error measurements. So given how important reliability is, what can we do to decrease error and increase reliability? We want to make sure that the instructions are standardized across all settings, if at all possible. That would reduce your method error. You could increase the number of items or observations, because the larger the sample from the universe of behaviors that you are trying to investigate, the more likely the sample is to be representative and reliable. In general, it is true, although nowadays we have more sophisticated ways of evaluating what we call differential item performance, but it is a general rule of thumb. And you see this tension too, especially once you start trying to administer different tests and measures in the real world, where time and effort, they're basically valuable commodities. Not everyone is going to have a whole lot of time to fill out a 100-item questionnaire. And so nowadays, a lot of items tend to focus on figuring out what are items that are functioning the best, and we try to get rid of items that are not functioning the best. But for the purposes of this class, in general, you should know that when you increase the number of items, you tend to increase reliability as well. Number 3 is to delete unclear items. Some people respond in one way, others may respond in a different way if your item is kind of wishy-washy, and so you want to delete those items. Especially for achievement tests, such as maybe a spelling test, for example, you want to moderate the easiness and difficulty of tests, because any test that is too difficult or too easy may not reflect an accurate picture of a person's performance. And you want to minimize the effects of any external events that may affect the outcome of your score. So if you foresee any particular external events that may indirectly influence how participants may respond to your questionnaire, you might want to postpone your assessment And so any external events, I'm trying to think of one example. One thing that I noticed, for example, especially if you've because sometimes what professors do is we recruit intro to psych students. I give them the opportunity to participate in research studies, right? And they can participate in research studies anytime throughout the semester, beginning, middle, or towards the end. Well, typically you start seeing a lot of error coming into the scores, let's say if there are surveys, at the end of the semester, because at the end of the semester, most students are quite stressed out because there's a bunch of things that they have to get done towards that. So they may not be paying as much of attention as they probably would have if they weren't as stressed out compared to the beginning or the middle of the semester. And so we kind of take action to try to weed out, remove any type of data that may not be of high quality, especially for data that's coming from students who may be feeling really stressed out and not really paying attention to instructions or the items that they're reading. So just stuff to be keeping in mind if you want to minimize the effects of external events. There are all kinds of other things that may affect the reliability of your items. So at the end of the day, the reason why psychometricians fuss about reliability is because if a test of measurement is not reliable and it's not measuring the same thing time after time, it doesn't really matter what it measures because it's not valid. And that really is the point at the end of the day. So for example, if you're looking at the effects of X and Y, and the test that is used to measure Y is not reliable, how can you ever know that X actually caused any change you see in Y? And if there is no change in Y, how do you know that it's not due to a poorly constructed test rather than the fact that X has no effect? So it's stuff like this that makes it really hard for you to figure out the outcomes of your test if your tests are not reliable. So the reliability of test instruments is essential to good science, no matter what you're studying. In our next chapter, we will learn that while reliability is a necessary condition for validity, reliability itself is not sufficient for establishing validity because you can be consistent but also be consistently wrong. So to learn more about validity, stay tuned for our next chapter. Right now, study the different concepts that we've discussed in reliability. Check out the question in the quarterly assignment, especially the one that requires you to calculate convex alpha. Have fun with that. Let me know if you have questions. And next week, we'll talk about validity. That's all, and have a good rest of the day, evening, or rest of the week.